Welcome to the concurrency session, and this is the most important session of POPL. It's not me saying it, it's Shaz Kadir saying it. Concurrency is pervasive in computing, concurrency and distribution. Moreover, for us academics, it is difficult, and its applicability is widening, its styles are changing. So plenty of research contributions there. The first talk is going to be given by Siddhartha and Ugur. They have promised, even though it's concurrency, not to talk concurrently. And it is a universal sound and complete forward reasoning technique for machine-verified proofs of linearizability. Thank you.
Thank you. Hi, everyone. I'm Siddhartha Jayanti from Google Research. My co-author, Yavuz, and I will be presenting this paper on possibility tracking, which is joint work with Prasad Jayanti of Dartmouth and Lizzie Hernandez of Microsoft. The informal and perhaps more informative title of our paper is A Simple Way to Prove Concurrent Objects. Let me start with the motivation. Asynchrony makes concurrent algorithms hard to reason about. In fact, subtle race conditions have plagued even mission-critical concurrent code. For example, concurrency bugs jeopardized NASA's Mars rover, were one of the causes of the Northeast blackout, and resulted in radiation overdoses that ultimately caused 3 deaths. The bottom line is that fundamental concurrent algorithms and data structures are deployed in all sorts of systems, including some which are critical to the life and well-being of people. Consequently, rigorous machine-verified guarantees of correctness are critical for concurrent data structures. In this talk, I focus on our technique for machine-verified proofs of linearizability. Linearizability is the gold standard for concurrent object correctness. In a concurrent system, operations run over intervals of time. In the picture, I've depicted an example run of a queue, which comprises of NQ and DQ operations by 3 processes that overlap in time. Linearizability states that while the operations take place over an interval of time, they must appear to take effect atomically, that is, instantaneously at some point between invocation and completion. In the example, these linearization points are marked in green. A straightforward technique for proving linearizability is through forward simulation. To prove an implementation, the prover maintains a copy of an atomic reference object. He considers an arbitrary run, and as the run unfolds, the prover identifies the linearization points of the operations as they occur, and shows that the return values of the actual implemented object match those of the atomic reference object. The example run depicted here can be proved in this way if the prover is able to identify the green linearization points as they occur, since the return values of 2 and 1 are consistent with these linearization points. But what if the last part of the run unfolded differently, and the last operation returned 3 instead of 1? Then the proof would go smoothly until the last DQ returns 3, but would fail there, since the atomic reference object would have returned 1. Does this mean that the run is not linearizable? Actually, no, the run is linearizable, just with different linearization points. Notice that the linearization point of the DQ in question did not change. Only the linearization points of the operations in its past did. In other words, we can't always determine the linearization points of operations as they occur. Sometimes our choice of linearization points for past operations may have to be future dependent. Future dependence is a key hurdle in proving implementations linearizable. It shows that the simple forward simulation proof technique is not complete. This leaves us with a question. Is there a simple proof technique for linearizability that's complete and can be used to obtain machine-verified proofs? Previous work since 1990 has made partial progress on this question. Many proof techniques beyond forward simulation have been discovered, including prophecy variables, aspect-oriented proofs, commitment points, and partial order maintenance. These techniques have been used to prove future-dependent algorithms, including the Herlihy-Wing queue, but most of these techniques are incomplete. Schellhorn et al. Showed that backward simulation is complete. However, this technique requires reasoning backwards rather than forwards in time, and is therefore unintuitive for algorithmists. So what do? We contribute the first universal sound and complete proof technique for linearizability that requires only forward reasoning. Our proof technique can be used to prove the linearizability of any implementation of any type. We call our technique possibility tracking, since it tracks all possible linearizations rather than just one, like forward simulation. We also show that a variant of our technique called single possibility tracking is complete for strong linearizability, a stronger criterion used principally for probabilistic algorithms. Finally, we demonstrate the efficacy of possibility tracking by giving machine-verified proofs of several data structures, including for the Herlihy-Wing queue and Jayanti's snapshot, which have been noted for their intricate future-dependent linearization structure, and the Jayanti-Tarjan union find object, which are widely used in applications such as clustering, model checking, and graph analysis. So how does possibility tracking work? We saw earlier that forward simulation is incomplete since the single atomic reference object it maintains may be insufficient to capture all linearizable future behaviors of an object. Our main idea is to avoid this pitfall by not maintaining just a single atomic reference object, but actually maintaining all possible atomic reference objects that correspond to linearizations of the current run. Specifically, to prove the linearizability of an algorithm A, we design an augmentation A star, which tracks the set P of all possible atomic reference objects corresponding to all possible linearizations. Thus, we see that A is linearizable if and only if P not empty is an invariant of A star. Proving this invariant is the possibility tracking proof technique. Let me clarify what possibilities look like with an illustration. Consider this run, visualized here until time t1. There are 3 pending operations. In this case, one possibility is that none of the operations have linearized. In this possibility, the Q object is still in its initial empty state. Pi1 and Pi2 have pending NQs with arguments 5 and 9, and Pi4 has a pending DQ. Another possibility is that Pi1's NQ alone has linearized. In this possibility, the Q contains 5, and Pi1's operation has linearized with a return value of ACK. In general, a possibility simply maintains the state of the object and a triple for each process. The fields of the triple are the current operation, its argument, and its response if it has linearized. A blank in the last field reflects that the operation is yet to linearize. A blank in the first field reflects that the process is idle. Other possibilities include just Pi2's operation linearizing, Pi2's operation linearizing before Pi1's, all 3 operations linearizing in the order Pi2, Pi1, then Pi4, and many more. The augmenting variable P will be defined to maintain all of these possibilities. But how can we maintain this set P as the run unfolds? Well, we simply update the set of possibilities as each new step of the system unfolds. For example, if the next step of the system happens to be Pi4 returning 9, then all possibilities that are inconsistent with this return event are filtered out of the set P, as they are no longer possible. For example, the black possibility suggested that Pi4's operation was yet to linearize. So it was filtered out since Pi4's response field did not match the return value 9. The remaining possibilities, which are consistent with the run until the latest step, are kept and modified to reflect that Pi4's operation is now complete and it has become idle again. Now I describe the full technique for maintaining P. This consists of initialization and 3 update rules. Initially, P contains just one possibility P naught, in which the object is in its initial state and all processes are idle. The 3 update rules are as follows. When a process pi invokes an operation, each possibility P is updated to reflect that pi is no longer idle and has invoked the operation op with argument arg. As we saw in the example, if pi returns r, then possibilities that don't reflect pi as having linearized with response r are filtered out, and the remaining possibilities are modified to reflect that pi is now idle. The most involved case is that of pi executing any intermediate line of code. That is, a line of code that's neither an invocation or a return. In such a case, we evolve each possibility p to reflect that any set of pending operations, that is, operations that are invoked and yet to linearize, can linearize in any order. This can lead to an explosion in the number of possibilities. But that's okay, since the augmented algorithm is for proof purposes only. When written out in symbols, the possibility tracking initialization update rules for maintaining the set P look something like this. So for a given algorithm A, the possibility tracking proof technique is to generate a machine-verified proof that P not empty is an invariant of A star. Now let me hand it over to Ugur to walk you through the Herlihy-Wing Q case study.
Hey folks, for our case study, I'll be talking about the Herlihy-Wing Q implementation, which was given as an example in the first paper that introduced the concept of linearizability. This implementation uses two base objects, X, which is a read and fetch and increment register, initialized to 0, and Q, an infinite array of read, write, swap registers, each initialized to bot. I will explain how NQ and DQ are implemented through an example run, and here I visualize the initial values of X and Q. X is set to 0, Q is set to all bots. And let's start our run by having a process NQ5. This process first fetches and increments X. Namely, it writes the old value of X into a local register I, and then increments X. So now X is 1 and I is 0. In the next instruction, it writes its argument into QI, in this case, writing 5 into Q0, and then it returns. Let's say we have another NQ, this time 10. The process once again fetches and increments X, and then writes the old value of X into its local register I, and then writes 10 into QI, in this case Q1, and then it returns. As for the DQ, we first read X into a local register L, and then start a loop from 0 to L with the looping variable J. We loop until we reach either reach L or find a non-bot element QJ. And in this case, Q0 is non-bot because it is 5, so the process swaps bot into its place and then returns the retrieved value, here, that value being 5. So say we have another DQ, we once again read X and start the loop. Now, since Q0 is bot, we move to Q1, and then as Q1 is not bot, we swap bot into its place and then return the retrieved value of 10. Now let's talk about what makes this implementation interesting, which is its linearization points. The DQ operation has a fixed linearization point, exactly at the instance where it swaps bot into a non-bot register in Q. And it might be enticing to think similarly about the NQ, but that's not the case. And through another example run, we will see that NQ's linearizations are actually feature dependent. Once again, we start with the default initial values of X and Q. And let's have a process P execute NQ5 to completion. And then let's have it NQ10, but pause after the fetch and increment line. And now let's have another process Q execute NQ15 to completion. And then once again, NQ20 execute completion. And now if we have Q executing two successive DQs, we note that the first one is going to remove 5 from Q0, and the second one is going to remove 15 from Q2. And then continuing with another DQ, this time examining how the process loops through the indices more closely, we see that Q0 is empty, so we move to Q1. We see that Q1 is empty, so we move to Q2. And now, instead of iterating further, if we pause here and instead continue the pending NQ by P, we will see that it writes its argument of 10 into Q1 and then return. And let's now consider what the possibilities are for the states of the implemented Q. And this is going to be a function of the upcoming DQ operations. For instance, if we assume that there's another process that comes in and performs successive DQs to completion, the first one will find 10 at Q1 and then return it, and the second one will find 20 at Q3 and then return it. And the return values of these successive DQs tells us that right at the instance we pointed out, 10 followed by 20 is a possible state, since 10 is returned first and 20 second. Let's make a note of this possibility. What if we continue Q's pending DQ? In that case, Q proceeds to Q3 and removes and returns 20. And then if that were followed by a new DQ, that would remove 10 from Q1 and then return that. In that case, 20, then 10 is very much a possible state as well. This is a little unusual, and we note that in the state 20 followed by 10, things appear in an inverted order compared to how they are present in Q. And this is something worthy of making an observation about. Specifically, Q3 followed by Q1 is justified as a possible state by the existence of this dequeuing process past index 1, whose looping range contains 3. And we can also talk directly about permutations of the non-empty indices in Q. Specifically, instead of talking about the justifiedness of the state Q1, we can say that the permutation 3-1 is justified by the existence of this dequeuing process. And here's an important insight. Since we have two possible states depending on how the future dequeues might be taking place, if we start thinking about the tracker, this tracker must contain possibilities with states corresponding to both 1-3 and 3-1. Otherwise, a future scenario might make P empty. And we can adapt the definition of being justified to a more general one if we say that any permutation of indices is justified if for any inversion we have a dequeuing process between the inverted pair. And now we can adapt our insight to the following statement. P must contain a possibility corresponding to each justified permutation of indices. And now let's ask the question of how does this insight help us with the proof? Well, we call that with our technique, we want to prove the machine linearizable through proving the non-emptiness of P in the augmented implementation. And let's also restate the insight. P must contain a possibility corresponding to each justified permutation of indices. Then it sounds like the key to prove that P is not empty is to prove that this set is contained in P. And that's exactly what we do. In our proof, we define a set S of possibilities, which exactly corresponds to this set, containing a possibility for each justified permutation. And then what remains is to prove that S is not an empty set, and it is contained in P. And this, in turn, implies that P is not empty, which is exactly what we want. And then moving on to the machine-verified proof, we prove this by induction, strengthen it with simple observations in order to make it an inductive invariant. And we can, this can be proven using any proof assistant. We chose TLA Plus and the TLAPS proof system. And specifically, if we express the augmented implementation in this specification language, TLA Plus, and then prove the invariant correct by induction, namely assuming it holds true in the current configuration, any line is going to keep it holding true in the next configuration. Yeah, this wraps it up for the case study. I'll hand it over back to Siddhartha.
So I think we'll just keep this conclusion up here and move to questions.
Thank you very much. I see a question here.
Hi. So, I mean, in these papers that relate linearizability with simulations, I mean, they start from restating linearizability as a refinement towards a specification, which in general is non-deterministic, and this is why you need backward simulations. Now, is it like your technique, like saying that it's equivalent to determinizing the non-deterministic spec using some subset construction and then reducing, now that you have determinized the spec, now of course you can use forward simulations?
So I'm not able to process exactly this path in my head and say whether that's exactly what we do. But we can handle, using this method, non-determinism and non-totality. So if the type spec is non-totaler, the algorithm is non-deterministic, or the type spec is non-deterministic, this can be handled using the possibility tracking method.
Yeah, I'm just saying that it looks to me like this possibility tracking is like determinizing the non-deterministic spec using subset construction. But
I see. It's possible that that's one way to view it. I would have to think about it more carefully to answer definitively, but that surely sounds like a possibility.
Thanks.
So Herlihy-Wing's classical paper, in their appendix, they define exactly the notion of possibilities, and they actually have an algorithm following exactly like what you presented. And they also apply the algorithm on the Herlihy-Wing queue. I don't know if you have tracked that, and I haven't so far I haven't seen any difference between that algorithm and what you presented now. Are you aware of that or not? The appendix of their paper.
Yes, so I am aware. So their algorithm is, of course, the same algorithm that we're proving here.
Okay.
The technique, to my understanding, is not the same as what they have. They also have something which they call possibilities.
Right.
But the proof technique that is used here is different to that.
It would be great to see what's the difference.
So I would have to take this offline with you, because I would have to look at that more closely.
last question, and Zhengdong should be setting up in the meantime.
Thank you for your talk. I would like to know precisely what you're proving. So if the examples you showed looked like they were proving linearizability of a concrete history. But when I think of linearizability of an algorithm, I'm thinking of linearizability of all the possible histories. So how does that work?
That's a great question. So the intent of all of the things that you saw up there is that you are considering an arbitrary run. So consider an arbitrary run, induct over the time steps of that run. And what the cases of the inductive proof will look like is there'll be the inductive step will have cases, one for each line. So if some process pi executes line 5, its program counter is there and executes it, we will show that the invariant, if it held before, will continue to hold. So this is going to be the general case. Okay, I think it's time to hand it off.
Yeah, please thank the speakers and